All right, hey guys. So, what I need you to have in front of you, so that we can discuss the topic of molecular geometry, right? The basic 5 different shapes that we are going to do in this class. You need to have your periodic table in front of you, and we're going to focus our attention on the very last page of the topics 4.3, 4.4 test review. Those last 2 questions, which are sort of a synthesis of everything. Okay? So, let's start and dig in. So we have H2S, right? And so what it's asking us to do is to draw a Lewis structure. It's asking us to then examine or analyze that Lewis structure to determine how many electron regions there are. And then of those electron regions, how many are bonding versus lone pair regions, okay? And then determine the approximate bond angle and the shape or the molecular geometry of that. Okay, so we're going to start with, let's just write our formula. We have H2S, dihydrogen sulfide. Okay, and step 1, as always, is to use our periodic table to figure out the total number of valence electrons we need to include in there. Hydrogen is in group 1. So we have 2 hydrogens, so I'm going to go 2 times 1 for those 2 hydrogens, plus sulfur, if we count from left to right, 1, 2, skip the middle, 3, 4, 5, 6 valence electrons. So I need to include a total of 8 valence electrons in there. All right. Sulfur is going to be my central atom, all right, because it has lower subscript. Okay, and hydrogen is never a central atom anyways. So I'm going to put a S here, right? I'm going to put an H right there, and an H right there. Okay, there's 2 electrons, 4 electrons. I need 8 total, right? I can't put any dots around hydrogen. Remember, hydrogen always is terminal, just gets a 1 bond, okay? So the remaining 4 electrons are going to go around sulfur as lone pairs. All right, now there is another video on how to do Lewis structures in the first place, right? This is just a quick run through that process. Now, we've drawn our Lewis structure. Now, we're going to analyze it, right? So the first thing I want to figure out is how many electron regions are there, all right? So remember, an electron region in this context is just simply looking at the central atom in our Lewis structure and determining how many different locations we have electrons. Now, electrons can be in a bond, or electrons can be part of a lone pair, right? So in the case of H2S, and the way this is drawn, I have an electron region here, another one there, another one in that lone pair, and another one in that lone pair. So I actually have 4 electron regions. All right, of those 4 electron regions, 2 of them are bonding regions, one here and another one there. Okay. Sorry, my phone's acting up. All right, and then 2 of them are lone pair regions. Okay, now hopefully you guys have notes or your flashcards in front of you to help you remember, right, what we would call this particular shape. So when we have 4 electron regions, right, 2 of them being bonding, 2 of them being lone pair regions, right, that corresponds to what we call a bent shape, right? So basically, if we were to draw like a ball stick model, right, with an S here, we'd have an H like this, and an H like this. It's that bent shape, right? Just like we did with the monomer. All right? And then whenever we have 4 electron regions, again, our bond angles can vary based on a lot of variables, not only the number of electron regions, but over there's 4 electron regions. We're going to say our bond angle is going to be close to 109 degrees, plus or minus 5 degrees. Well, usually when there's 4 electron regions, we're going to be somewhere in that range. All right? So that is H2S. Next one is silicon dioxide, SiO2. Okay, so same steps here. Silicon has 4 valence electrons. We have 2 oxygens, so we're gonna go 2 times oxygen, which is 6. Okay, and again, we got that from our periodic table, but just by counting the columns left to right, skipping the middle. So we got 12 plus 4, 16, all right? We're gonna go silicon as our central atom. Lower subscript, also lower electronegativity, right? I'm gonna draw a line for an O, another line for an O there, all right? So I need to put all 16 of these electrons in, and we always start on the outer atoms first and then go to the center if there's any left over. So I've got 2 electrons with that bond right there. 4, 6, 8, 10, 12, 14, 16. All right, so in this case, I don't put any dots or any lone pairs on the central atom because I used up all 16 on my outer elements first. And I want us to use that as a guiding rule. It's a really common mistake you guys are making is you're trying to put lone pairs on the central atom when they don't belong there, all right? Fill up the outer elements first, then when we run out of space, if there was still some left over, then we would put lone pairs on the central atom, all right? So we got all 16 of those electrons, all right? We filled up oxygen, and that oxygen, all the electrons are in there, but we still don't have an octet here, right? And so we can do that in several ways, right? So I only have 2, 4, right? So I'm gonna have to add 2 more bonds to my central atom to get it to its octet, right? And the most common way to do that, right, would be to go 2 double bonds. Although theoretically, we could do some resonance structures if we wanted to, and go like a triple bond on one side and keep the other at a single, or we could go a triple bond on this side. Okay, but if we did our formal charges, which again is a previous video, this one would be our best one, just FYI. All right, so we got that done. We got our octet around the center, right? We got octet around everything. All 16 electrons are accounted for. We got our resonance structures in there, all right? Now, it is worth pointing out that all 3 of these resonance structures end up with the same number of electron regions, same shape and everything, all right? So in this case, for electron regions, I'm just gonna write E dot R, all right? We're gonna look at silicon, which is our central atom. I have electrons here and here. So I have 1, 2 electron regions. So worth pointing out, whether it's a single bond, double bond, or triple bond, still counts as just 1 region. So I have 2 electron regions. 2 of them are bonding regions. I have 0 lone pairs. And again, for these questions, I'm only looking at the central atom. Yes, there are lone pairs on our outer atoms. We're only concerned with the central atom, right? So I have 0 lone pairs, 2 electron regions, 2 bonding regions, 0 lone pair. This would be a linear shape, okay, with an angle of 180 degrees. Again, we'll just throw our plus or minus 5 degrees on there just to indicate that possible range.